Okay, this next part of our chapter 3 is something that's pretty handy to have in those situations where you're looking for a zero of a function and you're looking at your function that you have to set equal to 0 and solve it, and you just can't think of any way to solve it. Okay, maybe it's just one of those that's hard. So usually what we would do is we'd end up graphing that function and having our calculator tell us where the 0 was. Newton's method is a way that you can do that without the calculator. But there are certain few conditions that has to be met. So in order to use Newton's method, your function has to be continuous between the values you're looking at. It has to be differentiable, which means there can't be any points. You can't have a function that does this, because that's not differentiable at this point. And there can't be any holes in the graph. And the function at your starting point and at your ending point have to have different signs. So for Newton's method, we've got a 0 somewhere between these two random points, okay? And that's what this last condition means, is the function at this starting point has to be one sign, and the function at the ending point has to be a different sign. That's just saying that we can see that there's a 0 between there, right? So we can see that, if this is my A value here, and this is my B value, I've got positive values here and negative here, so I know for a fact that it's going from positive to negative, which means it's crossing 0 somewhere in there. And you can find that either from looking at the graph or just noticing that your values are positive and turning negative. So Newton's method is based on the fact that if you have a 0 of the function, that 0 should be close to the 0 of the tangent line. So I'll kind of draw a picture of what that means. Okay, let's say we've got this blue function here. And somewhere between, let's say, 0 and whatever value this is up here, so this could be my A, and this could be my B, it's crossing 0. Newton's method says that if I drew a tangent line, okay, this is going to be my first point that I'm going to guess where the 0 is. It's clearly not there, but it doesn't matter how close you are for your first guess. I'm going to guess that it's here. Newton's method says that if I drew a tangent line in at that point, so something like this, okay, there's my tangent line, that the 0 of this tangent line, which would be right here, should be close to the 0 of the actual function. And it is pretty close. Well, what we want to do is we want to find out what value this is. Okay, so this is my x2, so that I can find the next point and then draw another tangent line in there and find out where that is. And if I keep doing that, these successive iterations of the same process, it's going to bring me closer and closer to this actual 0. So what I'm going to kind of do is show you where Newton's method came from, just using this diagram and some algebra that we know to come up with an equation for the next x value. Okay? So I want to know the equation of this line. Okay, and specifically I want to know when the equation of this line equals 0. Okay, so my y value, I want y to be 0. So if we look at our point slope form, y minus y1 equals m x minus x1. The things we can plug in are y, okay, I want to know when that's 0. y1 is actually my function at x1. Okay, it's this y value here. Because if I'm plugging in the value that I'm using as my first guess, the y value I'm getting out is the function at that value. So this is the function at x1. That's going to equal my slope. Okay, my slope here, slope of the tangent line, is the first derivative at this x value. So m is really f prime at x1. X is this. I want my next x. Okay, so x is really what x2 is. I want to know what x2 is. And then I'm going to subtract x1, which is still x1. Okay, I want to know what x2 is. I want a formula for that so I can easily get my next x value that I'm going to use. So I'm going to solve this thing for x2. So I don't need this 0 here. And I'm going to divide this f prime over. So I'm going to have negative f at x1. So the function's value at my first guess divided by my derivative at the first guess now equals my next guess minus my first guess. So I'm just going to add my first guess over. So I've got x1 minus the function at that divided by the derivative at that point. And this will equal my next number that I would use. And I do the same process. So if we replace 1 and 2 with ends, so if we say, if I pick a guess, okay, maybe it's the 5th number that I've gotten out of this, and I subtract the function at that x value divided by the derivative at that x value, that's going to equal the next x value I should use. So the x to the n plus 1. Okay, so it could take us from 1 to 2. Then I could use 2. Okay, put 2 in. So the second x value I get would give me the next x value, the third x value. The third x value would give me the fourth, the fourth, the fifth, the fifth, the sixth. And what's going to happen is I can keep repeating this process and keep getting these tangent lines. So if I just we'll draw another tangent line in here. Okay, this one looks like it'd be something like that. Okay, that's going to give me the next x value, which would be right here. Okay, this would be like x3. If I draw another tangent line in there, oh, that's not a good one. Okay, I'm going to get closer and closer to this actual 0 value, which is, where the blue line is crossing, which is right here. I'm just going to keep getting closer and closer. So this is the formula for Newton's method. So make sure you have that written down. And I'll kind of show you, I've got an animation of how this actually works. Okay, so there's our first guess, there's its value, there's the tangent line. So that's our next x value. Here's the value at that x value, here's the tangent line. Here's our next x value we're going to use. Here's the function at that value. Here's the tangent line, another one. Okay, and each one of these is getting closer and closer to the actual 0. So let's apply it to a real function. We're going to use it on a function that we actually know the answer to. So I can just solve this one to find where the actual zeros are. So if I set this equal to 0, I'm going to get 0 equals x squared minus 5. So 5 equals x squared. So x equals plus or minus the square root of 5. So if I just type that in my calculator to get a decimal value out, okay, I'm going to get plus or minus, I'm going to write down all these decimals. 2.236067977. So if I start doing this, I'm going to start getting numbers that are closer and closer to this, and you're going to see that my decimals are going to start matching more and more of these decimals as I keep iterating further and further and further. So for my first guess, okay, I'm looking at this, and I see x squared minus 5. I want that to equal 0. Well, maybe 5 is pretty close to 4. So maybe to get my first guess, I would say, well, it's got to be close to when this function is 0, which would be at plus or minus 2. So I'm going to pick 2 for my first guess. Okay, so my x1 is going to be 2. So I'm going to take that first guess and subtract the function, so this function at that value. So if I put 2 in here, I'm going to get 2 squared, which is 4, minus 5 is negative 1, divided by the first derivative of this. So I need to know what y prime is. It'd be 2x. Okay? So I want the first derivative at 2. So that'd be 4. Okay, and this gives me the next value I would use. So 2 plus a fourth is 2.25. Okay, that's my next x value. So I'm going to take that one and subtract the function at that value, so 2.25 squared minus 5 divided by the first derivative at that value. So it would be 2 times that, which would be 4.5. Okay, and I've already matched 3 decimal places just after 2 iterations of this. 2.236. Okay, now in most realistic applications, 3 decimal places, is close enough. But just to confirm those 3 decimal places, because they were different from this, I'm going to do it one more time. Okay, so I'm going to take that. Let's see if I can convert it to a fraction to make it a little easier to remember. Okay, 161 over 72. So I'm going to take that, subtract. Oops, actually I need to plug this in. So I need to plug that into the function, so I'm going to square it and subtract 5. I get that. Then I need to divide that by the first derivative at that, which is just this thing times 2. Okay, and then I need to take 161 divided by 72 and subtract what I just got. You get 2.236067978. So after just 1, 2, 3 iterations, I'm matching pretty much all the decimals that I had. Okay, so at this point I would have this much of it guaranteed since that didn't change. So I've got 3 decimals guaranteed to be, correct. I think, I'm not sure if significant figures applies here, but it seems to be the right phrase. So that's how Newton's method works. And this can be used anytime that maybe you don't know how to solve something, but you kind of have a guess at where it should be. So this is more of a practical application of calculus. There are certain times when Newton's method won't work. Okay, so if you think about our conditions in order to use this, the function has to be differentiable. So if it's not continuous or differentiable, then it could fail. The other thing you notice is in the formula here, we're dividing by f prime at a certain value. So if f prime at that certain, x to whatever it is, x to the a, if that ever equals 0, then it'll fail. The solution to this problem is just pick a different starting value, or one that's a little bit different, because then it shouldn't equal 0, and you can keep going on with the method. So there's a quick fix to that one. If I plug in 5 and I end up dividing by 0, I could pick 4.5 instead and keep going. There's a formula to make sure. If you want to see another example when it fails, there's one laid out in your book pretty well. Example 3 on page 231. But this is the formula that we use to ensure that it's going to work. So when x is in the given interval that we're looking at, if you take the function times the second derivative divided by the first derivative squared, if that's less than 1, then that guarantees that Newton's method will converge, which means it'll eventually get to one number. It'll be working towards that one approximation. And that's everything for Newton's method.